We have one last little bit here with polar area. So the thing about polar area is when we look at the area for a polar function, we're going to be looking at what's called a sector area. So the area of a certain sector of a graph. And we're going to use sector area because we're dealing with circles because it's polar versus rectangles when we're on the Cartesian plane when we're looking at boxes on that grid. So we're going to be looking at sectors. So the area of a sector is given by the equation 1/2 r squared, so 1/2 times the radius squared. Uh, you'll see that kind of with pi r squared, which is why we're taking our radius and squaring it. And then we need the angle. So the angle that we're looking at in this case is going to be theta, and that's just our angle that is that arc that we want. So how much of an angle is that arc? So just like with our function, we're going to be looking at the integral is of our sector area equation. The only difference is our equation is in terms of theta. So what we're going to be doing is using theta as our bounds and still taking it with respect to theta. So in order to find the area of a polar function, we have our area is equal to, we have theta 1, theta 2, so our two angles that we're looking between, 1/2 r squared d theta. So this first problem, write an integral expression for the area enclosed by the polar curve of r equals 3 theta plus theta squared on the interval from 0 to pi. This one's not too bad because it gives us r, it gives us theta 1 and theta 2. We just need to put it into an integral. So our area is equal to the integral from, we have theta 1 and theta 2, 0 to pi, of our function r. So 3 theta plus theta squared. And all of this is being squared. We're going to be integrating it with respect to theta, so this is our expression. We could type this into the calculator and get an answer for this, but we don't need to. We call certain polar graphs roses, and it refers to petals of a graph. These petals are all generally symmetrical and look very specific. So we're going to look at the polar function r equals 3 cosine of 2 theta. So the first thing I'm going to do is I'm going to show you what the graph looks like. So 3 cosine 2 theta looks like this. So it's called a rose because of the petals on the function. We look here and we can see 4 petals specifically. If I wanted to find the area of all 4, I could look at a couple different things like the area of just 1 petal or the area of half the petal and kind of extrapolate from there. Some things that you may notice is that the distance, the length of the 1 petal, the farthest part out is 3, which comes from the 3 times cosine of 2 theta. So our graph that we're dealing with here is going to have the highest x and y value of 3. But every time it comes back to the center. So it's going to look something like this. Okay, one of the things that you may want to kind of look at is just how this changes. If I were to change the 2 at all, we now get a different shape. So if I change it to a 4, we now have more petals. The amount of petals we have is going to be based off of the theta, or the things inside of sine or cosine, in order to kind of get us here. And part of it has to deal with our function, because sometimes our function doesn't necessarily have to be 0 to 2 pi. If I look at 3 theta, we actually are only going from 0 to pi instead of 2 pi. But if I look at 4 theta, I'm going from 0 to 2 pi. And what that means is this graph right here, 0 to 3 pi, it only takes between 0 and pi to get through every single loop here. And if I were to go from 0 to 2 pi, I'm just covering this area twice. So some things that we need to know is how to kind of figure out these bounds. One of the things that we're going to know is we generally want to use either the 0 or kind of those edges. So in our case, we would either use 0 or +3, -3. In order to solve, we are going to go ahead and just set whatever number we're using equal to our equation. So we want 0 or the edges to be what we use for bounds. So for instance, if I wanted to use 0, 0 is equal to 3 cosine of 2 theta. If I get rid of the 3, we now have 0 is equal to cosine of 2 theta. And I know 0, cosine is 0 when we are equal to pi over 2. So when that inside piece is equal to pi over 2, we are equal to 0. This also happens at 3 pi over 2. If I want to get theta by itself, I would do what we would normally do, which is divide both sides by whatever is happening with theta. So in this case, it would be 2. If I divide both sides by 2, I'm going to get pi over 4 or 3 pi over 4. And this is just telling me what angle to plug in. So if I know I needed to start at 0 and end at 0, I might try pi over 4 to 3 pi over 4. We just need to be careful. If I were to show our graph again, this one's going to be from 0 to 2 pi. If I go from pi over 4, we're going to see here, this gives us one pedal. So it's giving us the start and the stop of our 0 to the next 0. So if I wanted to find the area of all 4 petals, I would need to know that I'm finding the area of one petal and then multiplying it by 4. 0 to 2 pi is generally a safe bet if we don't know what's going on, but we do need to be a little bit careful because sometimes it's not necessarily what we want. But no matter what, when we're looking for our bounds, we want to pick a radius that we want to find, set it equal to our equation, and then solve, and that's going to give us some bounds. Sometimes when we have a graph, it actually has an inner loop. So if we want to find the graph of the square root 5 times the square root of 2 minus 10 cosine theta, this one's not a rows. It is going to look like this. So we have this big loop and then an inner loop. It kind of looks like a lily pad in a lot of ways. So things that I'm going to notice, the biggest value on this side is going to be a little bit bigger than 17. The reason why is because I have 5 square root of 2. If we take the most away as possible, it's going to get rid of, or it's going to add this negative area, or add this negative value, and it's going to move all the way over to kind of create that point that we want. This loop crosses right here at 0, 0. So 0 is going to be kind of important for us when we're solving for these bounds. So when I look here, I know my value is somewhere over here, and then I have a loop here, and then my inner loop stops about here. So if I were to look at what I have, we're going to have a graph that looks like this. It's not one of my best graphs. In order to graph these polar coordinates, a lot of times we're going to pick a bunch of points, plot them like we'd normally do, and then connect them all. So this part says, let the region R bounded by the inner loop of the limacon, this one right here, 5 square root of 2 minus 10 cosine theta, set up the integral expression for the area of R. So we know we need an integral expression. I know I'm going to need the area is equal to our bounds. We need a 1/2 times the square root of 5 times the square root of 2 minus 10 cosine theta squared d theta. And then we need to find our bounds. So our bounds here, we need the start and the stop. I know the start and the stop of this function happens when we hit 0, so I'm going to take 0 and set it equal to 5 square root of 2 minus 10 cosine theta. And then I want to try to get cosine theta by itself. So we have 10 cosine theta is equal to 5 square root of 2, and then we're going to divide both sides by 10. So cosine theta is equal to square root of 2 divided by 2. 5 divided by 10 is 1/2, so we get the square root of 2 over 2. The square root of 2 over 2 is a unit circle value, so we want to look at when cosine is equal to the square root of 2 over 2. And this is where having that graph is a little bit helpful. So if I look at our graph, I only want that little piece. If I start here at pi divided by 4, and I end it at 2 pi, we're going to see that we're only getting half of that little loop that we want and all of the big loop. So I don't want to start at pi over 4. We may want to end at pi over 4. Okay, so if I start at 0, I'm only getting half of this loop. The other half of that loop was ended up at that 2 pi mark. So if we go backwards just a little bit, and by a little bit I mean the exact amount we went forward, so pi over 4, we are going to see we get just this loop here. So that pi over 4 we want on both sides. So our interval is going to be negative pi over 4 to pi over 4. And then just double checking one thing, totally forgot the 1/2. So 1/2 times that integral. The worst part about polar functions and integrals with polar is finding those bounds.